Here's a problem about a moving point. A rod of length 12 slides so that one end stays on the x-axis, the other on the y-axis. A point P sits on the rod 1/3 of the way from A. It splits the rod 1 to 2. As the rod slides through every position, P traces out some curve, and we want the area inside it. Before doing anything, it's worth noticing what stays fixed while the rod moves. The two ends are always exactly 12 apart, one on each axis. That's the one thing that never changes here. When I'm faced with a problem like this, I usually start with the easiest point on the rod, the midpoint. Call A's position A and B's position B. The midpoint's coordinates are exactly half of A and half of B. The one condition that never changes, a squared plus b squared, 144, immediately becomes a circle. P isn't the midpoint, but it's the same game. Its coordinates are 2/3 of A and 1/3 of B. Turn that around. A is 1.5 times P's x, and B is 3 times P's y. Put that into the same condition, a squared plus b squared, 144, and it becomes x squared over 64 plus y squared over 16 equals 1. Semi-axis 8 along x, 4 along y. No calculus anywhere in that, just a circle stretched unevenly. An ellipse's area is just pi times its two semi-axes. 8 times 4 times pi, 32 pi. Here's the part that stops being a coincidence. The semi-axis in each direction is just the distance to the opposite endpoint. Pick any point on the rod, its distance to B becomes the semi-axis along x, its distance to A becomes the semi-axis along y, every single time. This has a name, the Trammel of Archimedes. People built actual tools out of it to draw ellipses, long before anyone had a computer that could plot one. See you in the next problem.